This is B. Naresh, working as assistant professor in AEC department. And today's topic is analysis of CG JFET amplifier, where CG indication is common gate JFET amplifier. So before going to this session, just I'm going to recall what is a FET, and we know that the FET is called as a field effect transistor. And why it is called as a field effect transistor means whatever the current generates in a FET, that is controlled by an applied electric field between the two terminals. One is between the gate and the source. Another one is source and the drain. So if you observe the FET construction and whatever the FET, we have the three types of the terminals. One is represented as the source, second one is a drain, and the third one is a gate. And out of these three terminals, the source is always give the charge carriers to allow the conduction in a field effect transistor. And based on the type of the material to use for the construction of the FET, and based on that, we need to apply a biasing voltage between the gate and the source, as well as drain and the source ends from that. And we also observe that from the characteristics of the FET. So we have the two types of the characteristics. One is represented as drain characteristics. Another one is represented as transfer characteristics. From these two characteristics, we identified that the drain current is a functioning of, so with respect to the biasing voltages, that is VGS, and another biasing voltage is VDS, where the VGS means the biasing voltage between the gate and the source, and the VDS means the biasing voltage is applied between drain and the source. So from these two characteristics, drain as well as the transfer characteristics, we identify that how the drain current is generates and how the drain current is controlled with respect to these two potentials. Hence, the FET is called as the field effect transistor. Now coming to the point, so where we are going to utilize this FETs means the FET can be the most of the applications we are going to utilize as a amplifier. And if you want to design an amplifier, we have the two types of the transistors. One is bipolar junction transistor, another one is the field effect transistor. In the case of bipolar junction transistor, we defined as when the transistor is configured in an active region, we can say that the transistor is acts as a amplifier. So in that configuration also, we need to define a proper operating point or a quotient point. At which point, so means at that point, at a quotient point, at a proper operating point, that particular transistor behaves like a good amplifier. To define this good amplifier, we are going to analyzing with a small signal model. So hence, so we are going to analyze the discussion of the common gate amplifier by using the JFET. So before going to discuss this amplifier analysis, we need to define a small signal model of the JFET. And from these two characteristics, what we observe, so from the drain characteristics or transfer characteristics, we observe that the drain current is a functioning of gate to source voltage as well as the drain to source voltage. Hence, from that, the ID from the small signal model, the ID is represented as Gm times of VGS plus 1 by RD times of VDS. So hence, let us consider if it is JFET, here I am going to take a N-channel JFET. Let us consider this FET contains three terminals. One is represented as a gate, one terminal is represented drain, and a source. And this can be modeled into a two-port model or a small signal model by using this mathematical relation. The mathematical relation is that is Gm times of VGS plus 1 by RD times of VD. And this is derived from these two characteristics with respect to Poisson's equations. And by using this mathematical equation, we are going to model into a two-port model network or a small signal model, hence. So let us take most of the cases. The source is this is the source is a common, and the input side here I consider the gate, and output side here I consider the drain terminal drain. Let us assume that the current is flowing from the drain to source, that is represented as ID, and we have the two current representations. One is GM times of VGS, another one is 1 by RT times of VDS. Hence, I am going to represent, and this is the current source model. Hence, it is represented as GM times of VGS along with another model that is across the internal drain resistance or AC resistance. Now we are going to observe a potential difference between drain and a source is represented as VDS, and if you want to observe the output, it is represented as V. Just take this is the gate, and here it allows the gate current IG, and this is the source. The current is represented as a source current. So this is a two-port model network or a small signal model equivalent circuit for a JFET in terms of small signal model analysis. Now we are going to discuss, so based on this JFET terminal representation, we have three terminals. So source, drain, as well as the gate. So we can configure, means the amplifier can be configured in three ways. One is by making so one terminal is a common for the input side and the output side. If a source is a common for both the cases, then it is represented as a common source amplifier. If a drain is a common, it is represented as common drain amplifier. If a gate is a common, it is represented as common gate amplifier. So means that, so either if any one of the terminal we consider as a common terminal, that is common for input side as well as the output side. Now we are going to discuss in this session, so what is a common gate amplifier and how we can define this common gate is acts as an amplifier by using the small signal analysis. And by using the small signal analysis, we are going to determine the three important parameters, like one is voltage gain, it is represented as AV, and the second one it is represented as input impedance, it is also called as input resistance, either RI or it is also called as ZI. And the third parameter is we need to define output impedance, and it is also called as R0 or a Z0. So these are the three parameters we need to find out. So to identify, so which configuration is acts as a perfect amplifier based on the gain parameters and the impedance parameters. See, to define this amplifier, we need to identify how much input impedance we need to offer and how much output impedance is required to satisfy the faithful amplification, means without distorting the given input signal. So coming to this a common gate or a CG JFET amplifier means gate is acts as a common terminal. So if the gate is a common terminal out of the remaining two terminals, source and a drain, so hence, so which one we are going to choose as a input terminal and which one we are going to choose as a output terminal. So when we consider the gate is a common terminal, now I'm going to consider the source is acts as input side and the drain is acts as a output side. So gate is a common for input side as well as the output side. So based on the representation, and when we are using this common gate, so that is the reason. So when we observe the common gate terminal, so we consider as gate terminal is a common. So this is common for input side and output side. Now I'm going to consider the source is acts as the input side or input term acts as input terminal. So across the drain, we are going to measure the output parameter, hence drain is connected to output side. And again, based on we require some amount of the biasing voltages. To understand these biasing voltages, let us consider the JFET. Again, in a JFET also, we have the two types of the JFETs. One is represented as N-channel JFET, another one is a P-channel JFET. So while constructing, so we are using some materials. So based on the construction, we classified as the JFET is the two types. One is N-channel JFET, another one is the P-channel JFET. If we consider the N-channel JFET, the source and drain is made up with N-type materials. In the N-type or N-channel JFET, the source and the drain is made up with N-type material. If it is a P-channel, the source and the drain is made up with P-type material. Here, I am going to consider the given JFET is N-channel JFET. So here I consider this is N-channel JFET, means that the source and the drain is made up with N-type material. Let us consider this is the drain terminal and this is the source terminal, and the inputs, this side is a gate side. So based on this representation, let us consider if it is the N-channel JFET and this is the drain and the source gate. And just now we discussed that the source and the drain is made up with a N-type material. And based on the terminals representation, out of these three terminals, the source is always gives the charge carriers to allow the conduction in a JFET. And if you want to repel the charge carriers or if you want to diffuse the charge carriers from the source to the drain through the channel, we need to apply some amount of the force in an external, or we need to apply an electric field between the drain and the source. And based on the properties of the field effect transistor, in a field effect transistor, the conduction depends upon only the majority charge carriers. Hence, the FET is also called as the unipolar device. And based on the property of the field effect transistor, now here we consider as a N-channel JFET. Hence, the majority charge carriers of the source are the electrons. In this case, the majority charge carriers are electrons. And if you want to repel the electron or this charge carrier from the source to drain, and we need to apply a biasing or electric field between the two terminals, that is drain and the source. Now we need to identify which type of energies are required to repel the charge carrier or to diffuse the charge carrier from the source to drain. So for this case, and we know that the electron is a negative charge particle. So for this negative charge particle, if we apply the same amount of force, then what happens? Then it repels the electron. So that is the reason. Source is biased with the negative pole of the battery with respect to the means to allow the conduction. We need to diffuse the charge carriers from the source to. So we need to diffuse the charge carriers from the source to drain. Means whatever the charge carriers are diffused or repelled, all the charge carriers to be attracting the drain. So that is the reason. So we know that the electron is always attracts the positive energy. Hence, drain is a biased with a positive pole of the battery, and a source is a biased with a negative pole of the battery to repel the charge carriers or to diffuse the charge carriers from the source to drain, hence to allow the maximum conduction in a JFET. So hence means drain is biased with a positive pole, hence that is the reason it is represented as a drain terminal is a biased with an external resistance, or it is also called as a load resistance or output resistance is a biased with a positive pole of the battery, that biasing voltage, here it is represented as VDD. And with respect to this, while we are applying this amount of the biasing energy, now we need to identify the potential difference between the two terminals, that is drain and a source, that is represented as VDS. Hence, so here I am going to measure the potential difference between these two terminals, drain and a source, that is nothing but a VDS. And similarly, now, so we need to apply a biasing voltage if you want to control the flow of drain current. Another biasing voltage is required between the gate and the source. So hence we know that gate is to control this flow of drain current from the characteristics of the JFET. So the gate is biased with the negative pole of the energy with respect to the source. It is called as the VG. Apart from this, now we are going to apply a amplifier principle, means the input is passing through the one of the terminal. So based on this common gate JFET amplifier, so in this common gate JFET amplifier, we consider as gate is a common terminal for input side and output side, and the source is considered as the input source. That is the reason. Across the source, now I am going to apply a AC signal or input signal, that is represented as Vin. So hence, so across the source, I am going to pass. This is the source. For this source terminal, here I apply the input signal, that is represented as Vin, and this is the AC source. So gate is a common for input and output. Hence, the gate is connected to lower potential, that is nothing but a ground potential. And output side, we need to consider the drain terminal. Hence, the drain is across the drain with respect to this output resistance, or it is also called as the load resistance. Across this resistance, we are going to measure the output voltage parameter, that is represented as V0. So this is a construction of a common gate, means the circuit representation of common gate JFET amplifier. So for this case, now we are going to analyze or to determine the parameters like the voltage gain, input impedance, as well as the output impedance. To identify these three parameters, we need to model into a small signal model. So if you want to model this configuration into the small signal model, so first we need to recall this circuit can be reconfigured into a small signal model analysis or a two-port model network analysis. For this case, I'm going to recall for the small signal model. So we know that ID is equal to GM times of VGS plus 1 by RD times of VDS. And let us consider the JFET simply is replaced with a small signal model. So initially we discussed how the JFET is replaced with a small signal model. So for this case, I'm going to consider, let us consider this is the gate and output side is the drain. And let us consider this is the source. And we have this a mathematical relation. The drain current is the flows. What is the drain current? It is represented as GM times of VGS plus 1 by RD times of VDS, and this is VDS. So this is a small signal model. And by using this small signal model and based on the approaching of this common gate JFET amplifier, we need to connect the external sources like your input parameter and output parameters here. If you look at this, the circuit of common gate JFET amplifier, the external input signal is passing through the source. Hence, I am going to apply across the source. I am going to apply a input signal V in, and it should be connected to ground across the source. And similarly, so let us take this is the gate and the drain. This is the source. So for the source terminal, we connected the input source. Hence, in a small signal model also, I represented the input signal across the source terminal. Similarly, if you observe this gate terminal in a circuit representation, the gate is connected to lower potential, that is nothing but a ground potential. Hence, the gate is connected with ground potential. And then, and coming to output side, so we need to measure a output across the drain, and while considering the load resistance, that is the RD. Hence, I am going to connect a external load resistance, or it is also called as output resistance, or it is also called as drain resistance. Across this, now I am going to find out a output voltage V0. So this is a small signal model for common gate JFET amplifier. So by using this small signal analysis of the common gate JFET amplifier, now we are going to determine the parameters like voltage gain and the input impedance as well as the output impedance. Now I'm going to calculate the voltage gain. So to determine this voltage gain, so we require this small signal model. So hence this is gate, just what we discussed just now. I'm redrawing the circuit. So let us consider this is drain. This is Gm times of VGS. This is small rd, capital RD. And here we are going to measure the V0. This is source. This is drain. Here the current is ID. Across the source we have some input parameter V. So let us consider, and from this representation, now we need to calculate the voltage gain. And before this, again, and from this from the circuit representation, we have the two impedances. One is internal drain resistance, another one is the external output resistance or load resistance. So whatever the conduction is that takes place in a JFET, that should be we need to allow into the output side. So for this case, so we know that the current is always flowing through the lower impedance. That is the reason we need to define that external impedance or output impedance should be very small compared with the internal impedance. Then only the maximum current is flowing through the output device. And based on that, now we are going to define the voltage gain. So we know that the voltage gain means it is defined as it is a ratio of output voltage to the input voltage V0 by V. So now we need to define in terms of the output voltage parameter as well as the input parameter. So from this circuit, we know that this V0 is equal to either IL, so IL into RD, or we can also write minus ID into capital RD. Hence, so then, and from this representation, so but we have the two impedances, that is the reason. So we consider as V0 is equal to ID times of RD. Small RD is a parallel combination with a capital RD. And from the circuit, if you observe from the circuit, let us consider the ID is represented as Gm times of VGS plus 1 by RD into VDS. And we made this assumption, if you want to allow the maximum current through only the output impedance, your internal drain resistance must be much greater than of your external load resistance, that is capital RD. Under this condition, and based on the property of the current direction, the current is always flows through the lower impedance circuit. Hence, and we are going to negate the maximum current according to this assumption. The maximum current flowing through this model Gm times of VGS. Hence, I assume this ID is equal to Gm times of VGS. So that is the reason here. From that analysis and from that a small signal model or a drain current model representation, we consider as the drain current is represented as Gm times of VGS. Hence, I am going to substitute this ID in this output relation, that is V naught is equal to Gm into VGS times of RD is a parallel with capital RD. Now I'm going to find out. So we know that from this, the V naught is represented as Gm times of VGS plus RD is a parallel with capital RD, where I'm going to take this VGS from the definition of the VGS, or so the means the potential difference between gate and a source. Hence, VGS can be rewritten as the potential difference between the gate voltage and the source voltage. So hence, VGS is also represented as VG minus VS. And from the common gate JFET amplifier, so we consider the gate is a common, hence gate is a connected to the grounds. So here the gate is connected to ground potential. So whenever the gate is connected to ground potential, means the voltage across the gate we consider as that is equal to 0. Hence, so here I am going to substitute the voltage across the gate is a 0, that is minus Vs. Means we need to find out the voltage drop across the source. And if you observe this circuit again, the voltage drop across this circuit, this is the Vs. So what is the voltage drop across the circuit? That is equal to your input voltage. Hence, I am going to assume, so Vs is equal to V in. Hence, VGS is equal to 0 minus V in. Hence, the VGS is represented as minus V in. So again, so this is actually minus ID. So then this is minus Gm. Hence, V naught is equal to minus Gm into this is, what is this? So minus V in is parallel combination with a small RD into capital RD. So hence, V naught is represented as Gm times of V in into small RD is a parallel with capital RD. Now, if you want to define a voltage gain, so what is the voltage gain? It is the ratio of output voltage to the input voltage. Hence, I am going to substitute V naught parameter and the VI parameter. Hence, V naught is Gm times of V in times of RD is a parallel with a capital RD by VI is a VI. Means this VI is nothing but V in is a get cancel. Then the voltage gain becomes Gm is parallel combination with RD, small rd and capital RD. Hence, we can rewrite this relation. Gm is equal to small rd into capital RD by small rd plus capital RD. And from this representation, so if you want to write, we know that condition is, so the two unequal impedances are in a parallel configuration. So the parallel equivalent resistance is equal to smaller resistance. Hence, and whenever, if you are assuming this small RD is much greater than of capital RD, the parallel combination of small RD and a capital RD is approximately equal to capital RD. From that, the voltage gain is equal to Gm into capital RD. That is for the voltage gain of the common gate JFET amplifier. So similarly, now we need to identify another two parameters like input impedance and output impedance. If you want to calculate the input resistance, so we defined as either Zi or Ri. It is defined as it is a ratio of input voltage to the input current. So means Vi means here I represented Vi and Ii means again this is I. So input side, if you observe the circuit of a small signal model, this is the gate and this is the drain side. We have the current representation Gm into VGS. One more is small rd, and this is the external resistance capital RD. And let's take this is the source. The source is connected to V in, and here this is Is. So now here I am going to observe the V naught. So from this case, what is the Is? input current, the input side, which current is the flows, input terminal is connected across, or input source is connected across the source side. Hence, the input current II is represented as IS. And in generally, from the construction of the FET, we know that IAC, the source current, is the summation of gate current and drain current. And from this representation, the gate is connected with a common terminal, or gate is connected to lower potential. Hence, the current flowing through the gate is a 0. Hence, we assumed as IC is equal to 0, then the source current is approximately equal to ID. That is the reason it is represented as VI by ID. And again, from the small signal model representation, we know that ID is equal to GM into VGS plus 1 by RD into VDS. When if RD is much greater than of capital RD, means the maximum current is flowing through only this GM times of VGS, hence ID is approximately equal to GM times of VGS. So now that is the reason I am going to substitute this one. So in the case of input impedance, that is Zi is equal to, or Ri equal to Vi by Id. So Vi means I am going to take Vin. Id means Gm times of VGS. Again, from this circuit, just now we observed this VGS is rewritten as the potential difference between gate voltage and the source voltage. And from this configuration, we know that the gate voltage is a 0, hence that Vs is nothing but Vn. So hence VGS is also equal to minus Vn. Hence this is Vn by Gm times of minus Vn. This Vn is a get cancel. Zi is equal to the reciprocal of transconductance. Zi is represented as 1 by Gm. So hence the input impedance of the common gate JFET amplifier is represented as the reciprocal of the transconductance. And similarly, we need to calculate the output resistance or output impedance. So from the output side, so let us take the V0 or Z0 or R0 is defined as, it is a ratio of output voltage to the output current when the input voltage is at V is constant or at VGS is constant. Hence, from the circuit, from the small signal model, at the output side, we have the two impedances, and here I am going to find out the Z0. So from this circuit, and we know that these two impedances are parallel combination, hence Z0 is represented as, so is represented as RD is a parallel with capital RD. From this, it is represented as Z0 is RD is a parallel combination with capital RD. Otherwise, you can substitute this V0 and ID. If you know this, what is the V0? We observed V0 is equal to Gm into V in times of RD is parallel combination with capital RD. Then you can substitute ID. So what is the V0? So V0 is equal to Gm times of V in is small RD is a parallel combination with a capital RD. And ID is I0 means ID is equal to Gm into VGS. When you are substituting this one, it is the ratio of output voltage to the output current. So means Gm into Vn. RD is a parallel combination with a capital RD by Gm into VGS. So this Gm is a get cancelled. From this circuit, we know that VGS is equal to minus Vn. So hence this Vn and the VGS is a get cancelled from this representation. So then Z0 is approximately is equal to small RD's parallel combination with the capital RD. Under this condition, and from this representation, let us consider if small RD or internal AC resistance is much greater than of capital RD, this Z0 is approximately equal to external impedance or external or load resistance, that is RD. So these are the parameters we observed by using the common gate JFET amplifier. So we'll see one problem for this common gate amplifier. Let us consider in a common gate amplifier, let RD is a 2 kilo ohms and GM is the transconductance is 1.43 into 10 to the power of minus 3 ohm inverse, and the smaller internal drain resistance is 35 kilo ohms. Evaluate the voltage gain, that is AV, input impedance RI, and output impedance R. So for this case, let us consider what are the given at here. They given that ARD means external resistance, that is 2 kilo ohms, and a transconductance GM, that is represented as 1.43 into 10 to the power of minus 3 ohm inverse or mos, and internal drain resistance is 35 kilo ohms. Now we need to calculate the voltage gain as well as the RI or ZI, and similarly we need to calculate either R0 or a Z. So if you want to draw the circuit for the given specifications while using the N-channel JFET, let us consider the drain is biased with RD, that is equal to 2 kilo ohms, and it is biased with some VDD. And similarly, the source side, we know that it is connected to input voltage Vin, and the gate is connected to ground. And here, based on these transistor properties, they given the transconductance is 1.43 into the power of minus 3 ohm inverse. So by using the specifications, now we are going to determine the voltage gain and input impedance as well as the output impedance. Let us consider the voltage gain. So what is the latest voltage gain? AV is equal to GM times of RD, what we observed just now. So from that I represented the voltage gain is represented as GM times of RD is parallel with RD means. So they given that GM is equal to 1.43 into 10 to the power of minus 3 ohm inverse. Small RD is a 35 kilo ohms and a capital RD is 2 kilo ohms means. Now I'm going to calculate this. GM is equal to, so 1.43 into 10 to the power of minus 3. RD, small RD is a parallel with a capital RD means we rewrite 35 into 10 power 3 into 2 into 10 power 3 divided by 35 into 10 power 3 plus 2 into 10 power 3. You can solve this one, it gives the voltage gain. So simplify this one, then the voltage gain is equal to 2.7. So they given a transconductance, they given internal drain resistance and external drain resistance or a load resistance. Based on these specifications, to simplify this analysis, then it gives the voltage gain is equal to 2.7. And similarly, we need to calculate the ZI or RI. ZI or RI, that is equal to the reciprocal of the transconductance. From the given problem, the transconductance value is GM is equal to 1.43 into 10 to the power of minus 3 ohm inverse or mos, hence 1 by 1.43 into 10 to the power of minus 3. That gives the input impedance, hence the ZI value is or RI value is 0.7 kilo ohms. So similarly, we need to calculate R0 or Z0. So we know that Z0 and R0, that is equal to the two impedances are parallel, that is small RD is a parallel with a capital RD, hence small RD into capital RD by small RD plus capital RD. So from the given specifications, we know that small RD is 35 kilo ohms and the capital RD is 2 kilo ohms, hence so 35 into 10 power 3 into again 2 into 10 power 3 by small RD again 35 into 10 power 3 plus 2 into 10 power 3. Then can solve this ratio. It gives that R0 is equal to 1.9 kilo ohms. So based on the given specifications, we identified the voltage gain, input impedance as well as the output impedance. So in this session today we observed that so what is a common gate amplifier and what is the small signal model of the common gate amplifier. So by using the small signal model of the common gate amplifier, we derive the parameters like voltage gain, input impedance, and output impedance. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.